How's Thanksgiving, Joey?
Pretty good.
You're just pretty quiet, I'm sorry.
Okay, so we're continuing on chapter 9. And chapter 9 is the first chapter is about chemical bonding. So in chapter 9 we studied the first chemical bonding theory called the Lewis bonding theory. And then in chapter 10 we will study the other two, the valence bonding theory and the molecular orbital bonding theory. Right, so today we are going to finish this chapter 9 and mainly talk about the formal charge from the Lewis structure. And then we're going to talk about the lattice energy, the pattern of lattice energy. And we're also going to study, use the Lewis structure, calculate the entropy change for the chemical reagents, or the delta H reagents, from the average bond energy. Right, I think we studied the first few sections. We learned a few like those examples and to like write the Lewis structure for the compound for the atoms, right? So when you write those Lewis structures for those molecular compound or those polyatomic ions, sometimes there is more than one choice. We call this kind of situation resonance. So usually you will see the resonance by distributing those double bond and lone pairs. Right, I think we did this pattern, and you find out this answer is B. You have two resonance structures. So you will probably see that you have two like the so-called major contributor. If you want to argue, you can have some of those resonance structures that's not that important. But as we talked about like last week, so sometimes those not a very important contributor is helpful or is also important in terms of finding out those reactivities for those guys.
Professor,
Yeah.
what number did we start on for chapter 9?
For chapter 9, I think we use a new standpoint.
Here we go.
Yeah, we use a new, just starting from the first one.
Okay.
So who need a new standpoint for chapter 9? Okay, so I think this is another similar pattern. So we have three compound of ions, and you do a practice, okay? Do a practice. So I think very important when you write the Lewis structure, or when you want to draw the Lewis structure, don't like jumping or rushing the steps. Okay? You first figure out how many electrons you have to available. So that's first couple of steps. You find out how many electrons, or you write out the structure. So with atom sample. Okay, I want to see like I want to see like your structure for all the three. So everyone do a practice. For ozone, it's don't draw those cyclic structure. Ozone have three oxygen, so just put one O in the middle, and then two O is the terminal. And similarly for that carbonate. Okay, so everyone do a practice. I want to see your practice on the Lewis structure. so what is the arrangement of the three atoms in ozone? You have three oxygen atoms, right? And you want to figure out one center. For three oxygen atoms, it doesn't matter which one is the center. You just make one oxygen in the middle and two oxygen on two sides. Right? So now you're counting the number of electrons, number of valence electrons. So you have three oxygen. Each oxygen has 6, right? Starting on the first one. Okay, so oxygen, let's start one on that. Oxygen, you get all the three structures. Okay, so that's good. You can. So if you don't use this, you only have 6 electrons for the middle. So therefore, you have to use one double bond. And you can use on this side and use on the other side. For the other one, SO2 is very similar, right? And so you can use that equal too. For the carbonates, very similar, right? Then you can find out how many resonance structures we have. Okay, what's the just write start by identify one oxygen in the middle.
I think I got, for the first one, I got 2, I think, I'm actually 3.
Yeah, you can see that 2 is the important one, right? And very good. You draw out. Don't just think about it in your mind. I think that's what you did for your second in design. Okay, so you get 2, right?
2 for those and 3 for those.
Yeah. You can value.
For this one.
You can get more for the last one.
Oh, you
And
have-
we'll see like which one is better if you get more. But that's don't draw the circle. Just pretty much just one in the middle. Very good for that one. So that will be the 3. Major contributors. This will be the 2. Do the last one. Need a little help.
There's no other ones for, oh, 3, right?
3, that's the basic structure. So you probably make sure the electron is right. 18 electron, that's right. So 18 electron, if this one has a 3 lone pair, that has a 3 lone pair, so with the bond, and so this is 8, that is 8. So you have 16. So probably we have 1 lone pair on the middle. And then obviously,
Okay,
so then you want to make sure everyone has, if they need orbitals, you give them orbital. Right? Oxygen need orbitals. A few those small atoms don't need orbitals. H don't need orbital, and boron don't need orbital. All right. So what do you think? What's the answer? Well, actually the answer is E or with them. Let me summarize like what most of you did. For the O3, you start with writing one O in the middle, right? And then you write another O. So right now, what is the structure? You can write this, or you can write something like this, doesn't matter. So later on, when we in Chapter 10, we decide what is the geometry. So then you were counting the total valence electrons. We have 3 O, and each O have 6 valence, so you have 18. And so then you will go to the next step. You will see you are going to distribute. So when you distribute, you have see like where are you going to put it first? The so-called priority. So very important is to have a structure. That means you want to have all those atoms together. So therefore, you just put one pair or one dash between the center and then the terminal. So then, once you finish this, you want to like complete octet, the so-called outside in. Do the terminal first. So this is the terminal. Right now this, so this O is outside, this O outside, so do these two first. And now in terms of the octet rule, so this is 2 electrons. And these 2 electrons, you can think about it belong to this O, and also belong to that O. So right now you need like 3 more pair for this O. And similarly, you need 3 more pair for this O. So then usually I will suggest you to like take a break. Once you finish all the atom, but there's one last atom have not finished yet. So then you take a break, calculate how much you available, how much you already used. So we have this much available, 18 available. Right? Now on this structure, we finish this one has octet. We finish that one has octet because they need octet. Obviously not in separation. Right? And only this one we did not check yet. And this is sort of the center. So what you do is just take a break now and counting, there's an 8 here, another 8 here, so you have 16 already here on the structure. So you do a calculation, so you minus 16, you have 2, so you have 2 more available. So whenever you have those more available, you will put on the center. And later on we'll say, even sometimes the center might have more than 8. And then you will check it. For some of those atoms, if they are in the period 3 and beyond, and so you can have more than 8, right? So you finish now. You finish to use all the electrons. So very simple, straightforward. So then you will see, even you have this. Put this one pair on the center, sometimes you still don't have an octet, you need an octet, right? So obviously right now this O, 1, 2, 3 pairs, only have 6 electrons, and oxygen is not in separation, so oxygen also need an octet, right? So then what you do, you will redistribute. You use so-called multiple bond. So you try to use multiple bond, you can do something like this. You just say like I want to like take that 2 pair away from not really a total away. I will redistribute that 2 and put it in the middle. So therefore you have one structure, something like this. And the other you don't use it yet, so you have this structure. Now you probably like wondering, if you do that, so then in this structure, everyone is happy, because everyone has octet and everyone needs octet, right? So 3O, all the 3O need octets. So right now here, this for example, this O, 1 pair, 2 pair, 3 pair, 4 pair, that's octet. The middle O, 1 pair, 2 pair, 3 pair, 4 pair, octet, and then that one we already know that's also octet. So that's it's kind of like one of those best structure. But probably sometimes you look at this problem and wonder, if you do this, you retake this from this O, and then why don't you do the same from the other? So therefore you will, if you mark this as your first structure, so therefore you get this, And if I change like that, and that's like my second possibility, so then second possibility you can do like this. Alright, and obviously you can leave this, you can leave that alone. You leave that alone, then one thing obviously that's not right, even before we study something, some other theory, is that misorbitat. Misorbitat, that's kind of, if you need orbitat, if the atom needs orbitat, if you miss orbitat, in reality, it's still possible, because the electron is always moving, but in terms of the possibility is very, very small. So therefore, usually you will draw the so-called these two in our major contributors to our Lewis structure. All right. So then you do the same there for the other two. All right. So I'm going to erase that and do this one. And this one is an ion. So you follow pretty much the similar procedure. So the carbon in the middle, and oxygen, 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 3 oxygen. So then you want to like find out the total number of valence electrons again. So one carbon give you 1 times 4, so give you 4. And you have a 3 O, that will give you 3 times 6, give you 18. Now you have this negative 2 charge. Okay. So you have a negative 2 charge and give you 2 more electrons. So you adding together, you get 24 electrons. So again, you distribute. And distribute, you have the priority. Okay? Don't forget, you don't have to rush them into like a triple bond or double bond. You just make one bond first. One bond, that means you will have a stable structure. Right? So then you will complete the orbitat. If they need orbitat, H you don't have to give orbitat. So therefore you just put a string up here for each O. And that. And usually the problem gives you right, you will have enough electrons to do that. Okay? So you will leave the last one, and then you take a break again, right? So then you counting how many already on the structure, 24, because there are 8 here, 8 here, and 8 here. So you have 3, 8. So 24 minus 24. And we have a 0 left over. So in the last problem, you have 2 left over you put on the center. Now here we don't have any left over. Right? So then you still have to check if the atom need orbitat. Use the so-called multiple bond technique. Right? So then you for this problem, and as we talked before, you can leave like this. If you leave like this, obviously that carbon only have 6 electrons. It's not really that stable. Probably in like a flash of time, it can appear as this, but most of the time it will not appear as this. So what you do, you can take one rod like that, and then you can take another like that, and then you can take 3. So therefore you have 3 structures. And then each structure, for this problem, your carbon so carbon is a period 2, so it's a kind of small atom, so you cannot have more than 8 electrons. You can probably sometimes have more than 8, but that's not that stable, not that important. So therefore, you will have the one possible structure. You will see like this. You have carbon, and O, and then O, and that, and you include this with a bracket. The other 2 is similar, and then. Any questions? Now for this one, one is interesting, also interesting. It's very similar for ozone.
Isn't C and A basically the same thing? When it
Basically
goes-
the same, basically the same. C and A is basically the same. But a little bit different because this center here is S. You see, S is like larger than O. Okay. So therefore, S can have more than 8. So what you get initially, you will get S. I think most of you get that right now. So you have this structure, and I think you have for this one, you will have 18 electrons that are available. You agree? Right? So 18 electron, I put 8 on this O, I put 8 on that O. So you do a calculation, you have 2 more on the sulfur. Right? So you can do like a few things. Again, this will be a really minor. If you leave this alone, so this will be really minor contributor. But you know, that S is not octet, and S is octet. So what you do, you will do something like this. You will see, I will use like 1O and produce a double bond like this, and I will do the same from the other O and produce a double bond from that. And obviously, we will see, you can also like try to see, produce something like this. Okay? Or you can try something like this. And you can also like use the other O. So there are many of those possibilities for the so-called resonance structures. Right? So therefore, for this question is E. So all the 3 can have more than 2 resonance structures. Now we'll go to the next section to study something called the formal chart, to see like when you have those kind of problems, okay, or some other problem like the hydrocyanic acid HCN. So you can even change like the arrangement of the atoms, and you will see like which one is more important. So it's very important, like the formal charge. Okay. Okay, so we already see this SO2, and one way to draw the root structure is a double bond, only one double bond, one single bond. And then other way is have 2 double bond, the other way have 3 double bond, 3 bond, 1 single bond. So then which one is better? Which one is the major contributor? You kind of get the idea called the so-called formal chart. So very straightforward, very simple. Once you have the root structure, and this is one useful needs of the root structure. You can get some idea of where is the positive charge, where is the negative charge, and then you can also calculate those delta H reactions. Right. So that the formal charge, you kind of compare like what the how much electron the atom brings in, and how much electron the atom have in the structure. Okay, the equation you want to use is I think we use the same terminology as from the book. You will see the formal charge equals valence electron minus non-bonding electron minus half of the bonding electron. Then you understand what we mean by the valence electron. The valence electron is for the free atom, which means the atom before the bond. And we talk about in this chapter is those main group, or called the A group. Called A group, right? For those A group that equals the group number. So that's what we mean by the valence electron, the first number, the first term. So then, for this reaction, right? All the three atoms is from group 6A, right? So if you want to calculate the formal charge for this guy, you will see that is the formal charge that equals, the first number will be 6. The reason for that is this oxygen is from group 6A. So then the second term, this what I mean by the non-bonding electron. Non-bonding electron also called the lone pairs. The lone pairs. And for this O, there is one pair, two pair. And now you don't use pair because here you just use individual electrons. So therefore you have pair minus 4. Got it? So these four come from 1, 2, 3, 4, 4 dots. And these 4 dots is not between two atoms, it just belong to this O. Right. So then there's 4 more electrons here. These 4 more electrons is not those non-bonding, they are bonding. So you have 4, but according to the rule, you divide this bonding electron by 2. So therefore, here you are minus half times 4. Right, so altogether you get 0. So sometimes we write 0 right nearby the atom. Yeah. Right, so then you can do a similar calculation for this sulfur. So we call that FC. 3 numbers. The first number is very easy to find out. Just equals for most of the, because we talk about most of the main group elements. And so the first one is the 6. Right. So then you're subtracting how many dots that is on the atom. For this sulfur, 2 dots. Okay? So therefore minus 2. Okay. Now this last one, it kind of you going back and forth, you counting how many total dots in the bonding line you divide by 2. Okay. So one easy way to you don't multiply, don't divide, is just to find out how many dash. So if this structure I rewrite, that will become O, like 2 dash, sulfur 2 dots, and 1 dash, and 1 O, and 3 pairs. So the last term, one easy way, you can still do like what I did for the first, for that. An easy way to do this last term is counting how many those dash on the atom. So 1, 2, 3 dash, that just minus 3. Got that? Alright, so then what you get is plus 1. So therefore I will write plus 1 here for this S. Okay. Right, now you do the similar for this O. So let me write here, so that's called FC again. Okay. So what will be our first number?
6.
That's 6 because that's O also from 6A. Right. Now minus how many, what will be our second number? The non-bonding electrons that come from the lone pair. Or I will change this a little bit. They're not the same as this. So it's from the lone pairs. Okay. Not equal to lone pairs. Alright, and so we want to calculate this one, right? So there's 6, also like 6 non-bonding electrons. Right. So then we'll continue with the number 3. Right? So as I said, one way to find out the last one is easy. Just find out how many dash on the atom. There's only 1 dash on the atom, so therefore minus 1. Okay. So altogether we have negative 1. Alright? Right. So therefore this O is negative 1. Yeah. So then you have this structure. See that you have 0 plus 1 for sulfur, 0 for that that O with double bond, and then negative 1 for this O with single bond. And I think that's very, very straightforward, easy. Right. So then you want to know like whether you did something right or wrong. One kind of like a very good guiding line to tell you very quick whether you did something right or wrong is if you get the formal charge for all the atoms, and if you calculating, for example, for this SO2, which is a neutral compound, and as you review, this is 0, this is plus 1, this is negative 1, right? So the sum becomes 0, because this is a neutral molecule. So therefore, you can get some idea you did something very right. If you calculate that formal charge for the ion, and then you adding together, that's what equals the charge number. Right? So then it's very important to calculate the formal charge because it's very useful. Right? And so it's will tell you which, for example, which those resonance structure is important, is called beta. So the beta structure have fewer formal charge, which means closer to the 0 is better. And that obviously for some problem you cannot avoid. Right? For the ion, because you have adding together equals the negative charge, positive charge for the ion. So there's always something, sometimes you will have the formal charge. And then you will see the beta structure will have the smaller formal charge. Sometimes you might have a tie, so you have a small formal charge from one structure and another structure from other one. Then you will see the beta is have the negative formal charge on the more electronegative atom. So this feel like a concept. We draw the blue structure, calculate the formal charge, right? And then we can use this 3 rule to decide which one is better. You can do that for the problem we talk about that SO2. So SO2 we have this structure again, and so this is 0, this is plus 1, and this is negative 1. Right? And we'll talk about there's some other resonance structure. We can think about the other resonance structure is the sulfur, and have that one lone pair and one O like that, have 2 double bonds. Right? So then you can compare which one is better in terms of you know that your real molecule looks like more like what. And you can calculate the formal charge very quickly for this guy too. Right? So this O are indicated by this arrow is same as this O. Right? So 2 lone pair and 2 bond. So this is 0, so that is also 0. Right? Right. So here is 0. Right, now let's calculate the formal charge of this sulfur. 3 numbers. Right? So first number is the group number for those A group elements. Right? Sulfur is 6. So then we're subtracting. Right? Subtracting those dots on the atom. For the sulfur, there are 2 dots. So minus 2. Now the last number. Okay? An easy way to find out the last number is counting how many bonds. So you find out how many bonds or how many bonds on the atom. And for this sulfur, there are how many bonds? 4. So minus 4. And that becomes what? Becomes 0. So 0. Right? What do you think about the formal charge for the right O? Right?
0,
Why 0?
for the same reason as the left one.
Yeah, the same structure. Have like 2 lone pairs, 2 bonds. Right? Right. So therefore we have 0. Now you can compare these two. Right? So you see like this one will make the so-called major contribution to your real structure of the molecule. use some terminology. You will see this is called the minor, and that's called the major. Right. So sometimes you can even use the former child decides, which isomer is better. And now this example, and you can this I don't have that isomer example. So this example you still have those just purely the resonance. Okay. What I mean isomer. Okay. So for example, H, CN, you can have H bound to C, and then bound to N, or you can have H bound to N, then bound to C. If the book did not talk about that, so I'm not going to talk about that in this example too. Okay? So what you just draw the Lewis structure, calculating the former charge, okay? According to the rule, and you will figure out which one is a better isomer. Now, what we talk about here is just the purely the resonance. Resonance, that means you keep the same atom framework, right? So you have OCN, 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 and all have the same like the atom structures. Get it? Okay. So then, let me just erase what I. Right, and then we will do a very quick calculation again, and figure out what the former charge for each atom. Okay. 3 numbers, right? Let's see, first this one. The first number is 6. Am I right? The second number is how much? Okay, so 6. There's 6 dots on it. Okay. And then the last number is how many dash on it? 1 dash. So therefore this guy is -1. Get it? Now for this, let's say for this C, right? What is the first number for this C? 4, 5, 6. Why is it 4? Group number 4. And carbon group 4A. If those elements is in the A groupers, just use the group number for the first number. Right. So then, what is the second number? How many dots on that carbon in the middle?
0.
0. Just 0. Now how many dash?
4.
Altogether 4 dash. Okay? 1 dash on the left side, 3 dash on the right side. So altogether have 4 chemical bonds. -4. And that's also 1. Also 0. Right? Huh? Right.
Oh,
So this N. Now this N, what will be our first number? N is in what group? Group 5A, so therefore you start with 5. And so then we start with everything. How many dots on the N? Yeah. So then we'll start with everything. How many chemical bonds? How many dash? 3. And obviously this is become what? 0. Now, as we said before, you can do a very quick check, see if you did something right or wrong. When we talk about this guy is ion, -1. So your former charge adding together must equal to -1. Right? So I think we kind of right, we have 0, 0, -1, so therefore we have -1. Right? So it's very, very easy. Just keep like practice. As I said, you already give the 2 middle term exams, so you started the CRE for those exams. And for the final is standard, American Chemical Society standard. I think basically those final exams also, those topics we already studied. Okay? So you just study those, again, CRE, and study those, at the end of each chapter, there's a several quiz for the third edition. It's a very good quiz. And those quiz questions, it kind of gives you some idea how the question is on the final. Right, so now you calculate this guy. So the first number is what? 6. The second number is 4. Last number is 2, so therefore it becomes 0. Right? Yeah. And someone like summarize, if oxygen has 2 chemical bonds, that means 0. You don't have to memorize those summary, because it's kind of like somebody chewing something like a video. But you just use like this very basic three numbers. Right? So what will be this carbon? So let's say this carbon will have the first number is what? 4, the group number, right? And how many dots on this carbon? 0. And how many dash on the carbon? So just 0. Right? And this N, right? What will be the first number for this N? 5, group 5A. And how many dots on that? 4. How many dash? So therefore you get -1, right? Right. So then you check that again, right? So you have 0, 0, -1. Right. Now do a quick calculation here. What will be this? What will be this guy? I think this one will be probably +1. Very good imagine. Why is it +1? What is it? 6 minus 2 minus 3. And then +1. Okay? Very good. How many on this C? 0. You just see that 0. And how many on this N? If you figure that out, that means right. When you have adding with -2 and then 0 plus 1 adding together will give you -1, right? You can calculate why is it -2 because of the 5, right? -6 minus 1 and give you -2. And now we have these 3 structure. So which one you think is better?
The first one,
Why the first one is better?
because oxygen is more germinated.
You get rid of this C, right? Why C is kind of like not the best. Out of pattern right away. Why C not the better one? Because you have some former chart is -2, right? And you compare that with -1, so that's one problem. And you have 2 former charts. You have -2 plus 1, and the first 2 only have 1 former chart, which means 0 is not a former chart, right? Okay. So then you compare A with B, as Maggie said, right? So these 2 A and B kind of tie, right? Why is it tie? Because you have a 0, 0, -1, and there is also 0, 0, -1. So now what it used to break the tie is see like the -1 is on what atom? So as Maggie said, the -1 is if the -1 and -2, so if the negative charge is on the more electronegative atom is better. And electronegativity, you don't have to memorize the number, you just see the pattern. You're going from left to right in the same period, it increases. And then you go from top to bottom in the same group, it decreases. Well, that's for most of the atoms. There's a few groups that's kind of not that good.
So the farthest to the left is most electronegative, or farthest?
Electropositive.
This is most. Okay, so right is most. Okay. And down is right.
Get down and low.
Yeah, so that's.
So right and down is the highest.
Right now.
Yeah, so you just try to like remember that pattern and what we talk about in these few chapters. The pattern is very, very important. And later on, we also sometimes use the numbers. If you want to use number, I will use a number. Very good. So therefore, what you see, the A is the best, right? That's pretty good. Do a very quick practice. So I draw the root structure. Now on the exam or something, maybe you have to draw the root structure, right? To make sure you know how to draw the root structure. So we have the root structure here. And then the question is ask you to get the formal charge for the elements, for all the elements.
Is it you?
Very quick, is you think E is right?
Mhm.
So you have, you pretty much, you see sulfur has 0 because it has 6 minus 4 minus 2. And the carbon is 4 minus 0 minus 4, right? Any question like this for the answer is E, right? Right. So this question is calculate the formal charge for the first chlorine and
Is it C?
first chlorine C0 and 0. Yeah, I think that's right. Very good, very good. So just remember, I said you don't have to memorize, if oxygen bonding to have 2 bonds, 0, and nitrogen has 3 bonds, 0, you can just remember that 3 numbers. The first number is the group number. Second number is how many dots on the atom. And then just first number subtracting, the second number subtracting by the third number. The third number is how many lines on the atom.
Divide by 2.
If you multiply the line by 2, then divide by 2. If you count how many lines, don't divide by 2. For example, this O, right? For this example, this O. So you will see the line or lines. Because we use lines representing the bond. So for this O, you just starting from 6, and then you subtracting by 4, then subtracting by 2. Otherwise, you have to multiply how many bonds you have, multiply by 2, then divide by 2. Right? You can like do something like not. I mean you. You kind of you just simply counting how many lines, how many there. Right? So that is one. I think that is the sort of the 2x tangent we talk about in this chapter 2, the Lewis theory. That 2 x tangent. One is the resonance, and then the other one is the formal charge. Right? So this section about this is handy. So that still belongs to the Lewis theory. Lewis theory. All right. So in this one example, that is to the exception of the octet group. And so some of the atom in the middle, if the problem we will write, if you find out those kind of questions that exist, so you really have those kind of molecular xenon F2. If you draw the Lewis structure, and you just follow the usual procedure, you will find out the central atom has more than extended, which means more than. Okay? Right? So xenon is in the center. Right? If you cannot find out who is in the center, just review that. Review that the first step. So kind of you hint. You never put like those H in the center. You don't put those group 7, 8 in the center. Except when you want to see some of those very active species, which means when you study those organic, sometimes you use those catalysts, and you can have some of those. Alright, so then if the one last hint is you put those less electronegative atom in the center. Fluorine is the most electronegative atom. So everything else is less than fluorine. Right? So therefore, you put that xenon in the center is reasonable. Right? So what is our next step?
Count the electrons.
So you want to counting the electrons. Okay? So we have 2 fluorine. That will give you 2 times 7. Am I right? So we have 1 xenon. 1 xenon. That will give you 1 times what? What is crystal? 8. See? I almost forget about that because I didn't see that for a long time. You know. So you have 14 plus 8 equals what? 22, right? So now you're going to distribute. Right? So first distribute is very, very important. You want to glue. Right? You want to make a model. Just take one piece and take another piece you want to put together. Just use one dash first, right? So then we will examine those terminal. Right? If the terminal not an H, and then one exception, so you want for most of atoms, if they are not exception, that means you need octet. So you just adding 3 more pairs. So then you leave the last atom, and don't worry about it has octet or not have octet, or maybe more than octet, less than octet. And do a check, right? So we have 22 available. Right now we have the octet for this fluorine. The fluorine needs octet. We have octet for this fluorine. This also needs octet. Okay? So how many here on this right side? 8. How many there on the left side? 8. A very quick calculation. So once you finish the octet, so everyone one vertex. Left side, right side, top, bottom. If you finish all that, it's not 8. You think about that as 8. So we have 16 on the structure. So you can minus 16, and we have 6 available. Right? So what do you do with this 6? Very good. Right side. Okay? You are adding them as a pair. We have 6. So we are adding like 3 pairs. Ready? Now obviously once you do that, you sometimes still worry about is we do it right? Do we have an octet? Do we have more than octet? Right? Right. So obviously right now this xenon has 1 pair, 2 pairs, 3 pairs, 4 pairs, 5 pairs. That means 10 electrons. Right? And 2 more than 8. So then you check, is that okay? So it's okay in terms of they will be stable if in the 3rd period or beyond or below. In the 3rd, 4th, right? Yeah. So xenon is our element of 5th period, right? So it is okay. Why we talk about this? Why is it okay? Why we say that it's okay if they are in the period 3 and beyond?
They tend to break a lot of rules.
Break the octet rule, right? Yeah. So where the octet come from? When we say octet, that means where is the octet that number? Octet is 8, and even though we put that in the quotation mark because for some atoms we'll break that rule. So there's some atoms need only 2, some atoms need 4, and some atoms need 6. Okay? To understand why those in the 3rd period and below is okay, we have to see where that octet rule come from. Come from those atomic orbitals. orbitals. Atomic orbitals, right? Okay, so you get that? What is 8? Where does 8 come from? What is the atomic orbital? That means S, P, D, and F, right? What is the maximum your S can have? What is the maximum the P can have? 6. What is the maximum 10 and 14, right? Now you get where the 8 come from? 8 come from where? 2 plus what is 8? 2, yeah. No, I think you jump one step, no? Yeah, so if you want to break that octet rule, that means it has more than octet, you have to use D. You have to use D. Now, every atom has all those orbitals, no matter they are small or big. Okay, all of them has those SPD. You probably you don't have that 1P or 2D, right? But they were somewhere they do have those D. The problem is when those atoms are so small and their D orbital, the energy is too high. Alright, so that's about a brief, like a kind of very naive explanation. So when the atom is bigger, then the D becomes lower, and then you can use it. Those all depend on the environment too. Depend on what atom your atom is bonding to. So you know that's obviously always 100% true. Yeah.
So every time you have extra in the at all, they always go in the middle.
Yeah, yeah. Usually you will leave like one atom, the last one. Sometimes you will have more than one that kind of in the middle. You can do like just leave only one, then just put on the middle. Then sometimes you go to work for your final result because that's your first kind of your preliminary result. So you think about what we do for SO2 or ozone. So we put that one pair in the middle of O, then O still only have 6. So what you do, if the O needs 8, you just use double bond. Yeah. Right. What about this question? Draw the best root structure for xenon F2. Then you will find out how many long pairs of electrons are on the xenon. You see we can draw a root structure for the xenon F2. What we just did, we not finished that, right? You have to put 3 pairs on the xenon. Oh, we realize we just did the program.
Is it C?
The D is in there. Let's see that what you got there. Alright, so that's it about that question about how much attention you want to study.
Is it B?
Choose the best root structure for the BF4, BF3. Now, when you have those kind of questions, 2 things you want to check. First, check the number of electrons.
24.
Yeah. So you want to have your result. Very good, 24. If your structure is less than 24, more than 24, by the way, it's not right. Then what do you do? What do we do for the second step?
Connect.
Michael, why you find out that B is the best?
Well, because for one, B is only 3, so it gives out 3. That's only it could be without being what's the word, like, without having too many like positive or
That's called the what?
formal charge.
He have the concept, yeah. So you do these two things, okay, when you can do the problem. If I give you a problem, you draw the little structure, obviously you just follow the few steps, right? Yeah, I think that's, if you use the first step, you use number electron, okay? For this problem, as Mike says, 24. Then you will see this one out of the picture, right? But this one gives you how many electrons?
They give you 28 of those.
28. This one gives you how many?
This one gave you 28 as well. I mean, sorry, yeah.
26. And this one also was 26, right? All right?
You're right.
You can use like the way you do that, do the quick calculation, is try to get 8. Okay? So here is 8, here's 8, here's 8, 3, 8, 24, plus 4, 28. Okay? Here you can take this bag, right? If you take this 9 bag, put on here, you get what? 8, 8, and 8, 3, 8, plus 2, 26. Similar for that, but that's very straightforward. That's what you do. Right. So now what are we debating is between A and B, right? So why not an A? I think you see if you do the calculation for the former charge, right? Former charge here, everyone is 0. You agree? Everyone is 0. It's very easy to check. For all the fluorine is the same. For this fluorine, you will have 7 minus 1. Minus 6, then minus 1. Minus 1. Okay? Now this one is for most of the problem is called the group of what? Group number. And this one comes from what? Come from the dots. This one comes from what? From the 9. Alright, so then you can also calculate for this boron. So the boron, what will be the first number? 3, group of 3A. How many dots? 0, how many lines? So 0. Right, so then you are calculating this fluorine, and you will find out that becomes plus 1. Right? Why that plus 1? That's something with 7, then minus 1. For that fluorine on top, minus 4 with the 4 dot. Okay? Now minus 1. Minus 2 with the 2 line. Right? So therefore you have a positive 7, negative 6. So therefore you get a plus 1. Okay? So plus 1 here. Okay? Now for this boron, and you again start with 3. Right? That group of 3A minus how many dots? 0. Then minus how many lines? 4. And then 3 minus 4 is negative 1. Right? So it kind of makes sense. See, like if you want to have a structure that's stable, that means you want to have the former charge if you cannot avoid. If you can avoid, try to avoid. If you cannot avoid, try to have the former charge on the more electronegative atom. And you compare, as we said, I think one thing you want to remember, fluorine is the most electronegative atom. So fluorine has the electronegative number of 4.0. It's way beyond everything else. The second place is arsenic, 3.5. And then you have nitrogen and chlorine, that is 3.0. So fluorine is very negative. All right.
Doesn't boron, isn't one of those exceptions that also gets just
Yeah.
3 pairs?
And you see, the come like everything come together.
Right.
So the use everything, and if your former chart theory is right, you should be able to explain some of the exceptions. Right, similar story. Okay? So use two check point. First you check the electron, okay? And then you check the former chart. Last one is D, right?
Is there?
Oh, the last one is D.
Oh,
This one? Oh, you said this one is A?
yeah.
What do you think? That one is A? I think that one is A, right? Yeah. Again, you first figure out the number of electrons. Right? What do you think, Ben? What is the total number of electrons that for the SO for the negative? Very good, very good. You think it's 32? That's also think it's 32? Well, where does 32 come from?
24 from the oxygen, 6 from the sulfur, and then 2 extra.
Very good. So you have 4 oxygen, each oxygen gives you 6, honey 4. Then you have 1 sulfur, also gives you 6. So you have 30, then you have 2 negative charge, that's 32, right? Yeah. So you check that first on the pair chain. You have those kind of pair chains. You check how many electrons on all the others. How many electrons here? Am I right? How many electrons here? I think that's 30. That's 2 less. Do you put back one here? Yes, you pair here. You put one back here. You have one there. So then you have 3 each, then 1 6. So you have 30. Right. How many we have here? Same story. If I take this bag, so I put a bag there. If I take this bag, I'll put my hair here. Get that? What I mean is like this. If I do this, use these 2 arrows, what you get is S, O, and O. We not do anything to this bottom O. And we did not do anything to the top O. Got that? So that's what I mean by the arrows. If I use the arrow, so I take that 2 electron away from that one bond and put it back onto this O. So therefore this O, there it has 2 pairs, now it has 3 pairs. Okay,
It's
get it?
30.
This kind of arrow technique is very important in the organic chemistry. This is one of the skills you're going to use, okay? The so-called arrow pushing. So you want to know the electron, how the electron in the chemical reaction, how they move. All right. So I think you left over. So this one is okay. You have 32, right? That one is okay. 32. So what do you use to tell the difference between A and B? You use what? So first, second is our former charge. The first one is what? Number of what? You first check the number of electrons, right? That's what we did, right? We said this problem has 32 electrons available. So this 34 not right. This 30 not right. Got that? And this one is also what? 30, right? So that's not right. And that's kind of like you know, the good questions. structure, you first do is check the number right. So then you will see like which one is better by use the former chart. Okay? A former chart, these all are the same. You agree? Okay. Now let me change the color. These all are the same. And then you do a very quick calculation. For this O, what are the three numbers again? The first number for O is what? 6. Now for this O, I circle in yellow, both of them have how many dots? 4, so it's minus 4. And then both of them have how many lines on it? 2. So therefore this is what? 0. So let me change back to the red. Now let's calculate the red O. What's the first number? 6. No matter what O you have, the first number is always the same because that tells you how many electrons the O has. Right? So then what is the second number for the O that I saw in red?
6.
That's 6. Right? Because 6 dots on it. Now how many lines on the red O? 1. So therefore we get negative 1. Okay, negative 1. Right? If you think our calculation is right, so what's wrong with the former chart for sulfur? 0, because you have adding together negative 2. Right? So negative 1 from that O, negative 1 from this O, 0, 0 from the top and bottom. So the middle sulfur must be 0. So otherwise you are not adding to 0. Do a quick calculation. I think that's probably easy. For sulfur, right? What's the first number? 6. What's our second number? 0. What was our last number? Why is 6? Just counting how many bonds. Usually, the loose structure, you are used those bonds between atoms. But some of those structures might give you something like those sulfur, O, right? If I do those kind of structures, then you know this means 1 line. 1 line. Right? Yeah, I think because most of the time we use lines, so therefore I will use line. That's really easier. Right. So you have let's say finish this, so this becomes 0. Right? And this is 0. This is negative 1. And this is 0. Get it? Okay. Now this O is I should not circle in this color. What color should I circle that O? I just erase. This is something like that. Right? Do you agree? In answer B, I circle this O in red because these two O are the same. Okay? So therefore the former chart for this all these 4 O here, it is what? Negative 1. You adding together, you get negative 4. Okay? So again, if we are right, the sulfur must be what? +2. The sulfur must be +2. And you know like that way, so this is 6 minus 0 minus 4, so get +2. And then you have negative 4 +2, that will give you negative 2. Right? So then, why let me erase those, do you agree? So let me erase those and let's see, so here will be 0, and 0, 0, negative 1, negative 1, negative 1, negative 1, negative 1, negative 1, 0. So why A is better? Remember that rule we said? Right? fewer formal charge is better, right? And how many formal charge you have in B? You have 491. How many formal charge in A? You only have 291. Right. So if you are still like kind of not very quick in terms of draw the root structure to calculation, do more practice. It's very straightforward, very easy problem. Okay. I know like I'm very happy to see like our education become more and more pushing like to the fundamentals. I saw like those the kids in like middle school already study those. Yeah, they in eighth grade kids they are doing those. Okay? That's good because I usually see like in the graduate schools most of the chemistry graduate students is from foreign countries. At the school I went, more than 1/3 of the students is from China, from other countries. Well, that's okay because I mean we can do better. We can like if you because I know like my classmates it's very good if you have the education here and they are very creative and have very good knowledge. So that's it. But you have to compete to get a good grade. So next about the bond energies. So once we know the bond energy, and when we use the Lewis structure, calculating one thing we already studied like a lot in this class since like chapter 6, right? So now we have another way. Okay? So if you draw the Lewis structure for all the reactants, you can do that many times for your organic chemistry if you study organic chemistry. I think most of you are going to do. So then you can see like what the chemical bond is breaking, what the chemical bond is newly produced, and then some of the scientists they measure out, they measure to break a bond, how much energy do we need, and then we can use this number as a kind of a very good line, but a very rough line to estimate our delta H. And those numbers you use called the bond energy. So you have a table. So those bond energy, obviously you cannot use exactly to your real chemical reaction because your chemical reaction maybe not in gas. Your chemical reaction maybe in water, maybe in some other organic solvent, right? And your chemical reaction maybe not exactly breaking the bond half and half even. And then you also depend on what atom your atom is bonding to. So you talk about breaking the bond between, for example, between carbon and carbon, okay? And then that depends on because carbon is usually the so-called four chemical bonds. So it depends on a lot of variables, but you can use those numbers as approximation. So those numbers is summarized in the table. And you can see here, for example, H and H bond is similar. We have one H and H bond. But between, for example, N and fluorine can usually produce one chemical bond, so therefore you have 3 pairs here. And then N can bond into some other atoms, 3 other atoms. 3 altogether, 3 atoms, 2 other atoms. Right? So that depends on what are the 2 other atoms bonding to this N. And your energy may be a little different than this 272, but we will use that as a very good approximation. Right? So therefore, if you can figure out in your chemical reaction what bond is broken, what bond you newly made, and break the chemical bond, you will see need energy. to make a chemical bond, you will release energy. Need energy means absorb energy. Absorb energy, as we studied in chapter 6, is positive. Release energy is negative. So therefore, we can use the number, either use them as positive or use them as negative, and do the calculation for the delta H. And if you examine those numbers carefully, you will also find out the pattern. The pattern is about those bond energy trained. So one pattern is the more electron between two atoms share, the stronger the covalent bond. That's obviously you have to see, you have to compare the like atom. Okay? So first time we compare between carbon, carbon, carbon. You can have 2 electrons between carbon called the single bond. You can have 4 electrons between 2 carbon, that's a double bond. You can have 6 electrons between carbon, that's called triple bond. And you can see the pattern like this. So the triple bond is stronger because you need more energy than the double bond. The double bond is stronger than the single bond because you need more energy. But you also probably notice it's not really double or triples every time. Because those bonds, the single bond is a little different. We call them, I think in chapter 10 you will see all those single bond is called a sigma. So this is the Greek letter sigma. And when you have those multiple bonds, double bond or triple bond, then you have one sigma. So this one, you have one sigma, then one called pi. And then this one, a triple bond. That means you all together you need 3 bonds. So one, again, only one is sigma. Okay? All the both the other 2 is pi. So you have 2 pi. So pi bond is a little weaker. So therefore, even though you have 2 bonds between carbon and carbon, but the second bond is not so strong as the first one. So therefore, you not really double this 347. If you double that, you get 694. That is 611. Right? Like that? Right. So now obviously those bonds do all different things. So you talk about this bond, here, 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 because carbon needs 4 bonds. So you might bond into H, 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 and H. So that gives you the ethane. And here you will bond into 4H. So with SN. And now we will talk about in chapter 10. So even though here its locus lines are the same, this C to delta H is a single. So therefore this is sort of the sigma. And this H, C is also sigma, so therefore it's also sigma. Now sigma sometimes are different. Okay? How do you know the difference? Because in chapter 10 you will see those, what does C use? Do they use sort of SP3, SP2, those hybridizations? Right. So for right now, we don't have to worry about that much, right? So if later on you need it, so you remember I mean, not that strange. You need it to see like those little different. Right. So this is about the pattern of the bond energy. Okay. So I will say you will be able to read this, to memorize the patterns. Okay. Now how you use this to the calculation for this guy, this you calculate in chapter 6 is very important, right? You just draw the Lewis structure and identify those bond you breaking, and those bond you are making. Okay? And so no matter the bond is breaking or making, and you will be able to find those in the table. So they are all in the table, they are all positive number. Okay? So now what you do, you just keep them as a positive number for those bonds that is breaking. Okay? Then you will just change the number you find out for the bond you just newly made into negative. And then you put them together. So the equation here is a plus. But actually plus those negative numbers. If you want, you think about the bond, you just see the bond broken, minus those bonds produced. But in that way, you don't change the numbers when you find those numbers in the table. Okay. Now we do the way what we said on this diagram notes. Okay. So you just draw the real structure, see what bond is breaking, and you keep those numbers as positive. Okay. Then you will find out what the bond you are making. Then you change those numbers into negative. Okay. Then you add them together, not really literally add. If you add a negative number, that means you solve fraction. Okay? I think we need see this example. Okay? So this example, you want to calculate the delta H for the reaction. Okay? Let's identify. Let's first draw the little structure for all those compounds here, or all those molecules here. Right? So this is medicine. So who is in the center? Medicine CH4, who is in the center? C. Okay. So you have H, and H, H, and H. What will be our second step? Counting electron. How many total electrons we have? 8. Okay, so we have 8 electrons, so I will just put 1 dash, 1 dash, 1 dash, 1 dash. And then I will try to complete the octet for those atoms is need octet. Do H need octet? No. So this equation, this problem finished. So you have that CH4. Right? Right? So then plus 2, don't forget the coefficient 2. You have 2 water. So water H2O. Right? Okay, now H2O, who is in the center? Oh, very good. And I have H and H. How many electrons are available for water, for one water? 6 plus what? 6 plus 2, 8. So I have 8, right? So I will put a 1 pair here, 1 pair here. Right? So then I will try, do we need to put more electron on H? Oh. So then, only this O we did not check yet, so we will take a break. How many electrons already here? 4. How many available? Okay, so how many left over? 4. What do you do to the left over? Yeah, very good. So you just put a dot, dot. Alright, so that's good. So we have these 2 reactants, right? Now we will see we have 4 H2. What do you think of the structure for H2? H and H. Right? Okay, H2. Now you see how many electrons are available? 2. That's so then we will see plus CO2. So CO2, how many? Who is in the center? C, and we'll write O, and O, right? So then how many electrons all together available? 4 from 1C plus 2 times what?
6.
Okay, so we have 16, right? Right, so dash, dash, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 8. So then usually what you do, you will finish the octet for O, then you check, right? Then you check how many left over. We have how many left over now?
4.
0. 0?
Oh.
Yeah.
Oh, for this one, yeah. So you have 16 available, then you have 8 here, and 8 here, right? Okay, so we have a 0 everywhere. So then when you do, you will do something like this. Remember, you can take this away, and I will take this away. Not really literally take it away. You take it away from that place, then you do what? You share it. Right? Alright, so this will be the loose structure for CO2. Right, so then let's see, we're breaking what bond? What bond is breaking? Do you think you will be able to identify what bond is breaking? We breaking, so breaking, there's a bond here, C and H. See the bond between C and H? Do we have a C and H here? So we break the CH bond. Yeah? And how many CH bonds did we break?
4.
We break 4 C to H. Let me put a comma here, so then you will break 4 C to H. Let's, again, you just see like what bond we have before the reaction. What we have before the reaction is H to what? H2O? Do we have H2O? We don't. Okay? How many, therefore, we break the bond between H and O? Okay? Now just be careful, how many bonds did you break? How many H to O bonds did you break? Very good, very good. So you have 2 here, H1, okay? Then you have 2 of these. So therefore you will have, so you also break, you also breaking 4 H to O. And those numbers you should use them as positive. Yeah?
One thing I was gonna ask about calculating the energy of the bonds.
Mm-hmm.
For like, I took the quiz at home and stuff, and they didn't provide us with that, like, the numbers between each
You
one.
use like use the number from the textbook.
From textbook, alright.
Okay.
So for like the test, we're gonna be provided with that stuff?
Yeah, on the test, yeah.
Okay, just making sure.
Okay, so now, we will just keep those numbers that for the bond that break as positive. Okay? So we said we break 4 C to H. What is the number for C to H? Can you see that? What is the number for C to H?
414.
414. Right? So therefore we have 4 times 414. Then plus 4 times the bond between H and O is what?
464.
Very good. 464. Okay, so we keep these 2 numbers as a positive number. Okay? So these 2 numbers come from the bond that is breaking. Okay? Okay, now we find out making. What's the bond we make? We make what bond? H to H. Very good. How many H to H bond we made? Okay, so we made 4 H to H. What is the number for H to H?
436.
Okay. Now, should we use 436 or use negative 436? According to one way, we just see that negative 436. Okay? Because you break the bond. If you break the bond, you need energy. So that means in the process of breaking the bond, or the bond breaking process, absorb energy. Okay? So that energy is positive. When you make the chemical bond, it's the opposite. Okay? So initially those energy in the chemical bond release. Right? Release, when we start in chapter 6, that means loss. Okay? Loss energy is negative. Right, so we have 4 times that. Very good. Now just be careful also about this small notation here. If you can see from the textbook. Okay? From the textbook, because we have that carbon to O double bond here, but you are not going to use that number. See here? The carbon to O double bond here. Okay? That means that is so-called carbonyl. So that carbon to O double bond, like in those acetic acid, and in those like the esters. So you have those like the kind of ester usually have good like good those C to O double bond. Now you have this little mark means that is only for those compounds. Okay? If you have that C to O double bond, like what we have here, C to O double bond, right? In the CO2, carbon dioxide, you're going to use 799, right? So 799. Now again, this is 799. So we use, very good, so we use negative. Now how many of this do we have? Yeah, so that's, for the first time you don't understand what we mean by that 799. Okay? That 799, that means it's the bond energy between carbon and O double bond, okay? And in the CO2. Then in CO2, you know you have two of this. Alright, so therefore you have these two numbers, and one number is plus, one number is negative, and that's a very easy calculation. And you just multiply and add, and so what we see the result on the next slide. So we have that. Like that? Or you want to see the calculation, the number? So let me use what I write. See here, this is the bond break, so you keep them at the positive. So pretty much just what I write. So you have 4 times 414, right? Then you have 4 times OH, which give you 464. So these two numbers multiply and add give you 35 over 12. Right, so then bond you making, right? You make a 4H to H. That's what you need to see, 4H to H. And you also make 2 C to O. But this 2 C to O is not in those like the acetic acid, it's in the CO2. Okay, so this number here, so then for acetic acid, which probably you will see those root structures sometime in your like one this lab, like that. So this is acetic acid. If you want any of the dots, like that. Now in this structure you have this carbon to O double bond, and this carbon to O double bond is not in CO2. So if you do the calculation for this one, you're going to use 736. Alright, so very straightforward. So if you have this number 3512 come from the bond breaking, 3340, negative 3342 come from the bond making, right? So 35 more than, 3500, a little more than 3300, so therefore you should get a positive number. So that is this line, right? So 3512 minus 3342 get about 170. So this is the scientific notation. Why we use scientific notation like this? But this number will tell you we will have those so-called significant figure. Right? And how many significant figure if we write 1.70 times 10 to the power 2? 3. Alright, so you have time to review those questions, like those will be on the final. So do a practice. So I give you the loose structure for all those molecules in the chemical reaction. And you just be careful to identify what bond breaking, what bond is making. let me see your calculations. What about the break? Much similar to what we did for example, right? You break 4 of those. You break 4 of the CH. And 2 of those O double bond. Okay. What the bond is making? CO double bond in carbon dioxide, right? And you also make the H2O single bond. How many CO double bond you making? How many? Very good. How many H2O single bond you making? Okay. Very good. Very good. Everything okay? You probably identify them around 4. Yeah, CO2, so you have 12 days. 799 times 2.
Oh, yeah.
And also here, so H2O1, how many altogether you have?
Oh, 4.
Yeah.
Yeah. Okay.
Yeah, so this will be the usual, you have to be careful, like what bond you are breaking, what bond you are producing, and you also counting the number right. Okay, so you have the structure, right? C to H bond here, no more here, right? So therefore, C to H bond is break, and you have 4 then, you are getting right, right? And then you have 2, you also see this O double bond, so therefore you have to write double. You have O singular, you make a mistake. See here double, then you just double.
So there's double two?
Yeah, there's double, O double bond. No, those are the diamond problems. So that one, okay, so CO double bond, you write a C double. You have to, then also be careful, double in what? This is double in what? This is CO double bond in this spectrum molecule. In the table you see here? No, here, that is usual. That is what I said in acetic acid. When you see the CO double bond in this one, what is this? CO2. This is CO2, this is carbon dioxide. So if you see the C2O double bond, you don't use that 736, use this, 799. Okay. I think you also get the number wrong, the one, that one should be 4, of those. So you have 4 days, 12 days, so you have 12 days, this is wrong. And so you have 4 days. So this is negative.
Oh, I didn't see the
So
two.
this is negative, right?
Yeah, that's all, yeah, I just didn't see the two.
And also, probably you know that you should keep this one also negative. For traveler, okay, for this traveler? Okay, yeah, so the answer is E. If you cannot get E, just check like what number you use.
Thank you.
Okay, you're welcome. So the number of bond is not right. So you have to say, did you get E?
Yeah.
Okay, good.
Yeah, I got it.
Okay, very good. Brad, you got E?
Yeah.
Oh, you got E now? You got E? You see that water bond in break? Right? Water bond in break. So you can see before the chemical reaction, right? Water bond are there. Before the chemical reaction, C to H bond in here. Okay? Now after the chemical reaction, we don't have a C to H. We don't have a C to H. So therefore, all the bonds in CNH is gone. Yeah. So now you will see how many C to H in one, C to H another one, 4 of this. Yeah. So then you just write the 4 C to H bond in break. So write you have 4 C to H bond. How many of that? 4. Yeah, 4 times. And so then we also have this. This is the O to O double bond. Right? So we have that before the reaction. Do we have O to O after the reaction? No. Okay. So therefore that also break. Right? How many of this will break? How many O bond we break? Very good. We have 2 oxygen molecules. Right, so then what you do is just for those bond break, you just very careful see the number is right. So that's the 4, that's the 2. Now you just use the positive number, C to H is 414. Right? So we'll take the 4 times 414 plus 2 times, what is the energy between O and O double bond?
498.
498. Like 498. Yeah, so you're adding these 2 numbers together. Right? Right. Now let's see what bond we are making. What do you think? Do the opposite. Right? So you will see what we have here and what we don't have before the reaction. So sometimes maybe not that simple because you will see you will have the carbon-carbon double bond become carbon-carbon single bond. So what you do, what that means is the bond that breaks is the pi bond. You don't know the energy is pi or sigma, so you probably just take the double bond totally break, then you just make a single. Then the net result is the result of breaking a pi. Right? Yeah, so just completely break everything if there's something break between some atoms. Right. So between carbon and O double bond, we don't have that before the chemical reaction. Right? So therefore we know we are making the C to O double bond. Right? Now C to O double bond is very special. Because this is the common functional group in organic chemistry. Then you know organic compound is everywhere. Right? So therefore, you have to know if your chemical molecular compound is not those organic one, it's kind of like a CO2, then you use the number that called for CO2. Right? So number for this bond for CO2 is 7, for one of these is 799. Right? Now because you are making, so therefore you don't need energy. Kind of strange. You're making chemical bond, you don't need energy. You make a chemical bond, the energy will come out. Get that? Right. I think at one point I say something wrong. I said when you make energy, the energy will come from the chemical bond. That's actually not right. So then you identify how many bonds you make. You make the CO2 double bond, but you make actually in one CO2 you make 2 of this, right? Right. So therefore you have to multiply this by 2. So I will multiply this by 2 from here. Right? Right. So then this will be a typical problem you will have. I mean you will have this problem. So you will see you have the H to O bond here, which is new. New that means you are making. You don't have the H to O bond before this arrow. Right? Now the typical problem is so you have 1 here, 2 here. Then you see you have only 2. But don't forget you have 2 the coefficients. Which means you are making 2 water molecules. So each one water molecule give you 2, right? So you are making O2H bond, right? And you will have 2 times 2, and put it in that way, right? So these 2, well, these 2 come from 1, 2 here. The other 2 come from this. You agree? Yeah? So therefore you will have so you have 4 times O to H. So O to H, you do the table to find out is 464. Right? Yeah, so just sometimes you just take a little time to like recognize, don't get too excited, don't get too frustrated either. So you have 464, and that is for the bond that you are making. So therefore this is negative. And again, that will be times 4. Right, so that's it. So I think out of these few numbers, right? So this is the two numbers you will have the positive. This number plus this number will be our negative. Right? So altogether you get E. Right? So very, very good. So on the test exam, just very careful. And then obviously, I depend on you. I'm assuming you'll be able to draw the loose structure for those guys. But otherwise, you don't know precisely what is breaking, what is making. Right? So once you have the loose structure, and you will see what is breaking and what is making. All right. Very similar practice. This concept.
Is it C?
Okay, let me see. 436. Mm-hmm. You see the C? So we break 436, right? That means positive. And plus, whatever we break. Whatever we break.
Half of the double O.
Half of the double O, very good. What do we make?
2OH.
Yeah, 2OH. And so that's OH is the 464, right? Yeah, you are right. So it's negative 243. Got that? Okay, so you will have this guy become H to H. Right? Okay, now this, we still have the half here. So this, but you know this O is become this, right? You want to complete the structure, obviously. How many long hair on each O shall you put? How many long hair on each O you have? Yeah, so this is, right now this is O2. You start from the beginning, just do something like this. Right? For O2. You start from this. So you just draw like 2O. Right? And then you counting how many electrons available for O2? 12. So right now you have hairs 2. So just put like this. That makes the octet. Okay? And then you will see how we have 12 available. So you always leave the last atom. You don't like do it yet. Just check see how many you have left over. So how many we have left over now? Minus 8. 4 left over. So I will put 1 here, 1 here. Right? Then we use all the electrons. Right? So now the problem, this one is okay, octet. What is wrong with this one? Not octet. So what do you do? You will take 2 electrons away. Okay, no, watch carefully. So I'm going to take these 2 away. Right? You don't really take them away out of the question. You take that away, you put it here. Right? Right. So now you have this structure. That means this one will have like 2 pair here, this one will have 2 pair here. And now in the table, they did not give you those details, right? They just tell you O to O double bond. You can just use that. Even though sometimes that might be, I think that's okay. So it's O single bond here. One example is this. You can have that, right? But obviously you can have O to O, the so-called peroxide. You can have something like this. You don't have to have all those carbon peroxide, but there's different peroxide. All the peroxide are very good oxidizing agent. You can use them to do some good chemical analysis. Right, so that's it. So we have this, and so then you will produce O to H to H. Right? And you don't have that two now, they just only one. Right, so I think that's very similar. You should be able to, did you get a C? Be able to get a C? Okay, so now let's write them out.
The product will be,
Yeah, you can think about that too. The product will be negative.
the product will be
Okay, so the product is O
O
to H, right? So we'll have 2 times negative 4CD4. Am I right? Okay. So then I will have 1 times 414, that is positive. Right? So then I will have half of this guy, right? Because this is 4, 9, 8. So I have half of that. You agree? Okay, so you have this is positive, and this is positive, and this is negative. And you should be able to get, that's 400, right? Yeah, so I think that's right. Question? Okay, so is the starting chemistry is I think that was the department chair, and he like he has a website, and his website starting chemistry is like a step by step, which means it's kind of you are building something, you cannot skip. It's not that you study something like literature, like English or something, okay? Or history. So if you study history, you can study the history of American. Then you study the history, you can generally study the history of the world, right? So you don't have to do like one after another one. I think probably you get it, but it's somehow like it just remind you. All right, so then this question is conservative. Right? So if you remember that delta H reaction, right, is kind of equal those, we call them bond energy, right? Bond energy of those breaking, right? And in the equation we use plus, right? But we change those numbers into negative. If you don't change those numbers into negative, then you can put a negative here.
Is it A?
Say,
Right. So now what will be the answer for B? For those endothermical reaction, the stronger bond is breaking, and the weaker bond is making. Oh, obviously, for B,
exothermic.
very good, that will be the exothermic. Okay. So the one section is a kind of review that one law we study in Chapter-6, the Hess's law, right? You still remember the concept of Hess's law? Hess's law is about what? You have a few chemical reactions, right? Let's say you have a 3 chemical reactions, right? And somehow you do some of those linear arrangement. Reverse them, or multiply by some number, you take 2 of them, and doing some of those, then you add them together, you get the other one, right? And this is about, kind of about that because one like step in some of those chemical reactions called lattice energy. And you cannot measure that easily. Cannot measure that easily. But you can measure all the other processes easily. Okay? And then you can calculate, use the Hess's law. Okay? For example, for this chemical reaction, so we take the sodium metal solid plus chlorine gas and produce a sodium chloride solid. Right? This is one like before we like study this energetics of this topic. Let me just review this one like topic that we studied in Chapter-6. What kind of chemical reaction is this reaction? There's a kind of a special name. Yeah, you can think about that as the combination reaction, decomposition reaction, like oxidation reduction reaction. There's also one special name what we study in Chapter-6, and that have something to do with that delta H, and we have the subscript F. So what do we call those type of reactions? Formation reaction. Formation reaction. And why is formation reaction? Formation reaction basically definition is you start with those stable element, and sodium is a stable format. I mean, NaS is the stable format for sodium element. Chlorine gas is the stable format of chlorine element, and you produce one of those guys. So this is the formation reaction. So this is the formation reaction of sodium chloride solid. Now let's go on to see in this chemical reaction, and you can imagine hypothetically there are a few steps. You can think about those steps as you support the mechanism. And this kind of curiosity, those curiosities are always wondering how you like starting from those reactants and produce those products. Right. So let's think about this a few steps. We're not going to see all the steps. So one step we probably will see that is must be is the sodium solid atom, neutral atom, become sodium ion. That is a reasonable assumption because in this NaCl, this compound is ionic. You agree? Ionic between metal and non-metal. So therefore, what happens to the sodium, it must change into ions because this is the ionic compound. So therefore, there's one step. You see, one step you change that sodium element, sodium atom, into sodium ion plus ion. Right? And then this is also a special reaction what we study in chapter 8. This reaction representing I think the information here representing what? okay, probably I get it. So I'm not exactly right. If I change this into G, okay, so then you will see this will be the reaction for the first ionization. It's kind of like that. So when you use that to estimate, so we say this is the ionization process. Then ionization energy, you can use that as estimate. So for this chemical reaction, we need energy in. Or this chemical reaction absorb energy, so therefore this is plus. Okay? Now what will be the other possible step you can imagine you want to put it in? What other step you are thinking that might happen in that overall reaction between that and that? Yeah, chlorine becomes negative ion. And so that will be a reasonable assumption one step. So you will take like that, and you will take so even though this again will not exactly matching this number, because when we define the so-called electron affinity, we will take a free atom. Okay? So you want to imagine this number, your chemical reaction should start with a Cl, one Cl atom gas, plus one electron, then produce one Cl negative ion in gas. So this will be exactly matching that number. Okay? But we can use this number roughly estimate that too. When we do that, obviously we miss something. Right? We break that Cl bond. Because there's Cl. So here when you write this guy, so you have Cl2, you break the Cl to Cl. So I use this number as a very rough approximation. So I'm very rough approximation. Right? So if you have these two steps, okay? So one step is endothermic, then one number is exothermic. If your chemical reaction, if that chemical reaction from there to that only have these two steps, whatever you think about that chemical reaction depends on only these two steps. Your chemical reaction over there, it will be endothermic or exothermic, according to Hess's law. According to Hess's law, if we assuming these two reactions adding together, we're getting that. Okay? And what do you think? Well, your reaction will be, your reaction on the top there, it will be endothermic or exothermic. Why is endo? Why is endo? Well, according to Hess's law, if these two reactions adding together equal to this, and you are adding all those delta H. So one delta H is a positive 400 and 500, the other one negative 250. So obviously you adding together, you still have a positive. Right? So then, what's in reality? What is the real measurements? You take a sodium metal and you put it into the chlorine gas, and you find this number. See here, this is called the delta H0F. Why that delta H0F? Because this is the formation of this NaCl solid. And that is a negative number. Right? So what are we missing? What are we missing?
The bond formation.
Yeah, the so-called the lattice energy. Because I kind of really push you very hard, force you to agree with me. I take that two small steps, adding together, get the top step. Now let's really do the adding, see what we get, see what we're missing. Right? So one step we see NaS produce Na plus gas and plus one electron. Okay. The other small step is 1/2 Cl2 gas plus one electron. Plus one electron produce a Cl negative ion in gas. Okay. Now if you really adding these two equations together, what do you get? Very easy to add, right? So this electron on the left side, this electron on the right side, that cancel out. What you don't cancel out is NaS plus half Cl2 gas produce Na plus gas plus Cl negative gas. In this is so this is the sum of that two equations, right? So we get this equation. In this equation, then you imagine that equation you want to get. Right? What do you want to get? What you want to get is the equation you want to get on top is Na solid plus half Cl2 gas produce what? Produce NaCl solid. Okay, now you figure out which one step we miss. From this to guy to this. Yeah. So that's the step we miss. And that step also have the delta H. Right, so that's the step we miss. Right, because we adding the two together, we get this. And obviously this one doesn't mention this. So that obviously it is reasonable you are assuming one more step, you take these two, simply adding these two together, produce that. Or you can just use write one more step, or draw arrow here, so these two adding together produce this. Right, now this, as I said before, so that will also have a delta H. Graphically, so that's what the reaction looks like. Those are the ion in the gas state. They are floating around with high speed in gas state, right? Has a lot of energy, has a lot of those kinetic energy, and also a lot of attraction because they have plus and negative. And they are not usually stable, so they will combine together, produce a solid. So then that process has, so just this simple process, this last step we forget, also have a delta H. So this also have a delta H. And this special delta H, difficult to measure because you can just simply produce some of those gas ion, okay, and get the reaction ready, then you just let them condense into solid, you measure how much heat you absorb. So this delta H is sort of the lattice energy. And you can just measure all the other process. And you are just starting by what we did here. You want to get from here to here. Then you assuming you have those different steps. And if you did a good work, so each of those small steps, you will be able to calculate or measure the delta H. Now only one step that comes from this to this, you cannot measure or you cannot calculate. Right? So then you can use Hess's law to find that out. Right. So therefore you have those kind of concepts. What you want to do is you don't have to worry about I give you some numbers and I want you to calculating that delta H lattice. I did that before in some other classes if I sometimes I feel like we need to. But usually we don't need to do those calculations because I kind of review what we learned in chapter 6. So then what you do, I mean what we want to do in this chapter is just try to do like a conceptual compare, right? And so that's lattice energy. So in this process, from the gas to this, that depends on this equation. And this equation has the top, which is the numerator, and the bottom. So I just want to study this. So we want to study, we can use this formula and do a compare. Do a qualitative compare, not really quantitative. Okay, so then, see if you understand what I emphasize that in one step, or that step we cannot really measure or calculate that easy, and that step we have the delta H that representing the lattice energy. Right? So for all those ionic compounds, and you should be able to see that equation representing those lattice energy for the crystal structure. You said that is D. So that's same as this step, right? So we have the gas, positive ion with the right number. And for this compound, we need one Na, and we need one Cl. So you take one of those ion, maybe plus 3, depending on the compound. Now for this compound, you need one Cl, and you need you need one Al, you need 3 Cl. But the definition for this kind of lattice energy, delta H, lattice energy, okay, is starting from the gas, and the gas produce the solid. Those crystal, those lattice ionic compound, most of that is solid at usual condition. Get that? Right. So what are all the other equations tell you? What the equation that A represents? A tell you is what kind of reaction? Yeah, it's again the formation of that AgCl3. And you just take that element, the stable element, Cl gas, and Al solid, and produce only one of those. So that's the formation reaction for the AlCl3. Got that? Now what is the second equation tell you? What kind of process the second equation represents? Yes, solid gas. It's kind of like if you move from solid directly to gas, called sublimation.
So the answer is D?
The answer is D. Okay? So as I said, you want to study those CRE, you study, if those answers make sense, you want to make sense, you want to see what they tell you. Okay? So what does C tell you? We just studying that how many bond break, how many bond making, what do we use? And then we get those delta H, what do you say? You know, how many bond break, how many bond make, we have those numbers in the table. What about that? See the question. Bond energy? Yeah, so that's it's kind of like the bond dissociation energy for that process. You take that one molecule and produce that. Right, so what's the last one tell you? What's the last one tell you? The electron ion, you sign from a gas atom, plus electron produce a gas negative ion, what do we call that? Electron affinity? Andrew, right?
Yeah.
Yeah, electron affinity. Yeah. So I'm not exactly measuring, I mean, the seed not exactly measuring, but yeah. So I'm going to do more than that. Right. So now we can use that equation and what I said is sort of the lattice E proportional. You don't have to think about equal, proportional. Q1 times Q2 divided by R. Right? So what is Q1 and Q2? Do you have any idea what do we mean by Q1 and Q2?
It's the attraction between
Between the opposite charge, right? Pretty much the Q1 will be the charge on one ion. And just as a compare, you can use +1 or +2. Right? So if I write AlCl3, right? And you can see Q1 and Q2. So give me some good idea. What will be your Q1, what will be your Q2? If I write AlCl3. And those will be the charge number for those ions. So Q1 you can see +3. And Q2 will be what? -1. Very good. And what is R? The distance between the two types of ion. Alright, so let's just use that. So if you remember that equation, the larger the ion, the weaker the attraction. What do we mean by larger ion is physically larger, which means the radius is larger. Okay. So then next I will tell you the larger charge. Okay. For right now, if I tell you the larger ion, which means the radius is larger. So if the radius is larger, then you have larger radius, then the distance between the two ions, the R, it will be what? So the larger ion, that tell you the R is what? Is small or larger? Is larger. Now where can you find this R? You find R on the top or at the bottom?
On
the bottom.
Bottom.
So you have a larger R, and then you will have a smaller lattice under here, right? Okay, where is 3 or 4? Where makes sense? And let's see those numbers. If you can read this table, right? For this table, we compare these 4 compounds. All these 4 compounds have the same negative ion, right? So we know that lattice energy proportional to Q1, Q2 divided by R. Right. For all the 4, let's see Q1 and Q2. What will be the Q1 and Q2 for all these 4 compounds? Let's see Q1 times Q2. You will see this +1 times -1. +1 times -1. Right? +1 times -1. Then +1 times -1. Right? So in that equation, on the top, everyone has the same top. Right? Now here is a very good example. We compare those larger ion, small ion. All the Cl is the same. So Cl has the same radius. Now the positive ion, you have lithium, then you go to sodium, then you go to potassium, then you go to cesium, and their radius is increasing because they are in the same group of group 1A, so on the top is smaller, at the bottom is larger. So therefore, the distance between the two ions you change from 241 to 348. Okay? So this number gradually increases when you go from this to this. And that two numbers on the top are still the same. Right? Now you see the result. So the lattice energy for that small one is stronger or is bigger, and for the larger one is smaller or is weaker. Any question? Now you know what we will compare next, right? So you have the top, you have the bottom. Usually you want to compare, keep the bottom the same, compare the top. Or you keep the top the same, compare the bottom. Right? So in the last slide, we compare those four that have the same top, and we compare the bottom. Now for these two guys, what do we have the same? What do we have the same? You still remember that equation? That lattice energy proportional to Q1 times Q2 divided by R. Now we have two compounds. We have sodium fluoride, we have calcium oxide. Now between these two, what are the same?
The total charge.
What are the, you don't add them. You add them, all of them become 0. Okay? So what do? You take them multiply. Okay? So you take the positive one times negative one, you get negative 1. So this one, you have plus 1, that times negative 1, you get negative 1. This is what we mean by the Q1 times Q2. Now this, for this one, the Q1 times Q2, that will equal to what? I think we should be able to figure that out.
-4.
Negative plus 2 times negative 2. You agree? That will be negative 4. Okay? So now what do you compare? What is the same? Can you read this picture? What's the same? Roughly the same.
The radius is almost.
Radius, I mean the distance here between calcium oxide is 239, and that is what? 231. That's obviously different, but approximately the same, right? So in these two examples, you compare what will make the difference because the difference on the top, roughly the bottom are the same. So what do you think? Which one will have a larger delta? This one will have a larger delta, or that one will have a larger delta? I will give the numbers. Next time I will not give the number. So I will just first ask you the question, then I will ask you I'll give the number. All right. So that's so we have this. Obviously, we have the top number, the bottom number, and in these two slides. So this slide, we keep the bottom number roughly the same. We compare what makes the difference because the difference on the top. The last one is the opposite. And these are the two extremes, right? So obviously not every problem will have these two ideal situations. You keep that bottom of the same compared to the top, or keep the top of the same compared to the bottom, right? So don't we like sometimes have those problems, the bottom and the top are the different, then what do you do?
What was the question?
You see about one question. The question is, if I have this slide, the bottom are the same. 239, 231. So this number is R, that's at the bottom. So the bottom is the same. Last slide, they all have the +1, -1, +1, -1, so the top are the same, right? These two slides become very simple. In reality, if I give you some question, your top will be different, your bottom will be different, right? So then for those questions, what do you do? Should you be able to also make some compare, or is kind of totally out of the question, you cannot do anything about that?
The ion charge is more important.
Yeah, that's what I want you to observe. Well, I want to change you to be a chemist. The chemist is very good in observation, find patterns. So you will see that that ion charge makes the difference. Why that? Because from this example, you see this Q1 times Q2 for one compound is -1, for the other compound is -4, right? So that's 4 times difference. If you check those numbers for the R, right, and you will never find those such a lot of difference. Okay? So your distance between the two ions might change a little bit. Okay? Maybe change like 40% or 50%, right? But you will not change like 400%. So this is 400% difference. Right? So now we are going to use that pattern, right, to solve this problem. In this problem, if I give you 4 compounds, obviously, and so these 4 compounds, some of them have the same top, and some of them have the similar R. Right? And now what do we do? As you said, so you first use the charge separate into 2 groupers, into a larger or small groupers, right? What we might use a charge. You just take the Q1 times Q2. Okay? So let's figure out what is let's say CaO and KBr and KCl and SRO. Right, so I'm going to change the color. Okay, so this Ca is what? This O is what?
-4.
Okay, so very good. So let me make the table like that right away. Okay? So Q1 times Q2. So let's see how we get the -4. So we get +2 from calcium, right? And from O you will get what is the charge for oxide?
-2.
Very good, -2. So therefore this gives us, so you -4. Right? You agree? Right, now let's do the same for the KBr. What is the charge for potassium? +1, right? And what is the charge for bromide? Br? -1. If you do the multiply, right, get -1. So don't just don't be confused. Just multiply this number. So you okay? Just so you have K again here is a +1, and Cl is what? -1, and this gives us that's just -1. SR is what?
Too close.
SR, do you agree is +2? Why SR is +2?
Because it's 2A.
Group 2A. And oxide,
Negative.
so -4. All right, so what do we say that we're going to do? First, use the charge multiply, okay, and separate into a larger group or small group. In increasing order. So I'm going to start in a small group here. Small and larger. Okay, so who will be in my smaller group? And who will be in my larger group? Which two? Yeah, so you will have this CaO that multiply gave you -4, right? And the other one is what? SRO. You agree? Why I put this into the larger group? Because they give me a larger Q1 times Q2. Q1 times Q2, even though not mathematically it's -4, is not very larger, right? So there's also -4. So I use -4 to put these two into the larger group. You agree? It seems not really agree. What two shall go to the smaller group?
What is the smaller chart?
The small child, what is the product of the small child? What when you multiply that Q1 times Q2, what is the small number? -1. Okay, so -1 comes from PBR, then -1 also comes from KCL. Now once you know that, right? So you will just use the other, what we're going to use. We use Q to tell the difference. What we have not used yet is what? R. So you have this equation like this. Now remember the R is at the bottom. So the larger the R, and the smaller the lattice energy. You'll be able to predict the R is large or small, even though you don't know those numbers, right? So now let's compare these two guys, compare PBR with KCL, right? So you imagine you have two like ions, and both of them have the potassium, so potassium has the same size. And what will make the difference is compare BR with CL. So who is larger? The number, the final result is larger, right? So in terms of the radius, BR is larger, because BR is at the bottom. Get that? So the R for this guy is larger, this R here. Get that? So if I want to put this lattice E here, if I want to put it into an increasing order, so let me change this. So I will put this sign here, do you agree? This sign means less than, right? So the lattice energy of KBR is less than KCL. What is the reason? Andrew, what is the reason?
The radius.
Radius.
Larger for BR.
Yeah, so you have the same radius for potassium, so that you have a larger radius for BR compared with the CL, so therefore that number is larger. But don't be confused, if you have a larger that, and you have a smaller this, because this guy represents this. Right? Drink some water?
No, I have hiccups.
Yes, drink water. Hold your breath.
Hold your breath for 10 seconds, my tooth goes into one.
Alright, so now we know both of them, so both of those smaller groups will mean they will be smaller than the larger group. So everyone in the larger group will be larger than those anything in the small group. That we call them group first. Right? So that tells you KBR is smaller than KCL, then both of them is smaller than these two guys, but you don't know what is the order of these two guys. Use the same idea. So what is the same here? The chart are the same, both -4. Very good, then O is the same. And what is the difference is calcium and SR. So who is larger in terms of radius? SR. So therefore, you want to put this final 4 in the right order, you do what? Switch these two, right? So we have to apply something. So SRO smaller than the CO. That make sense? Alright, so that's the example, okay? So you can see, review what we did. We first use the chart separated into larger groupers. I did not write the second. Second, you use the radius and to tell the difference between those something in the same group. Really not that difficult. Right. So then let's see if you understand this. Okay? So this, even though we did not do that very similar to the example, but roughly you want to put this, you want to find out who has the highest. That's one, the kind of one of the problems, right? So what are the same, what are the difference? The highest one? You mean the highest, what, highest latest energy, right? Okay. So what you mean the Li, right? So what you want to compare this one, okay? Look, this one has the formula proportional to Q1 times Q2 divided by R. Get that? Right. So now you make a list. What is the Q1 times Q2 for all the four? What is the Q1 times Q2 for all the four? -1. So you have +1 for Prussian, -1 for BR, so that gives us -1. You agree? And now what will be the chart for this NA? What is the chart for NA? +1 or +2 or -1? +1, so +1. Now what will be the chart for BR again? The same, -1. So you have -1. Now what is the chart for this Li? They're all from group 1A. So again +1 and -1, we have -1. Even the RB. Which group is RB? 1, so therefore it's +1. Then you have -1. Then you have -1. Alright, so that tells you the top are the same. Then divide by, let's say, those different R. Right? So which one will have a larger R? Whichever have a larger R will have a smaller this guy. Or smaller this guy. Because the top are the same. If you have a larger R, you have the same number divided by a larger number, you get a small number.
Li would have the smallest radius.
The Li is on the top, have the smallest radius. Then you have the smallest radius Li, put together with the BR, then the distance between the nuclear of Li to the nuclear of BR is getting closer, because the Li is smaller. And this I is about the distance between the nucleus of the positive ion and the negative ion. Very good, so you should be able to get that very easy. I can see the result, right? See the result. Forget about the negative number in the mathematical science. So you have -800 compared with, just think of those numbers, 800 compared with 700 compared with 600, so that's obviously that is the highest number. So now you do what I did in the example, right? So in these three, you will have a different R, you also have a different Q1 times Q2.
Is it B?
Let me see. Increasing magnitude. You said what?
B? It's the other way around.
I think E makes sense, right?
Yeah.
So Li. Any question? Any question? What do we use to the first? What do we did? Right? So these two in our larger lattice energy energy group. And that by itself is our smaller lattice energy of the video group just by itself. Right? And what do we use to first classify these two into larger or smaller groups? What do we use? How do we know these two will be a larger lattice energy? Use the chart. Alright, so that's. Now we talk about the last section. It's very important. It's about the electronegativity and bond polarities. Right? So electronegativity is another pattern, is another number. So it's about an atom to attracting the bond electrons to itself in the chemical bond. And then you have this pattern, you go like in the same period, left to right, and gradually increases. Then in the same column, in the same group, the top to bottom gradually decreases, even though if you examine this table, you will see there are some of those exceptions. So those, again, forget about those transition in the meters. So even those group, this is group 1A, and here is group, so those are the A group, and here is the A groupers. So obviously here you will see those exceptions and exceptions, right? But those exceptions are not that important, okay? So usually you talk about those, for those, between those, those non-metals and metals, you can just use our patterns. Left to right increases, bottom to top increases. So then, and you can solve some problems. So if I give you some questions, give you a few elements, and you'll be able to find out the order. Make sure, so you pay attention to those words. Increasing, that means smaller to larger one. Small words, larger words. Okay? Alright, so obviously this electronegativity, okay? So for those metals, so they are small. Right? What do you think? See that C makes sense? Yeah, so the answer I think is a C. Let's check. Okay? So let's first compare BE with SR. So what do you think? Between BE and SR, who will have a larger that electronegativity?
SR,
SR, why SR?
the bond.
Right on top. Very good. So then let's compare SR with TE. Right? SR and TE, what do you think? Where is the TE and where is the... They are in the same period. Right? Yeah, in the same period, and TE is to the right. So therefore TE has larger. Very good. Then let's compare TE with SE. Compare T and SE, they are in the same what? The same group. Same group, that means the top, the one on the top of it have like a larger electronegativity. Is SE on top of TE? Good. So then let's compare that SE with the CL. Then that's a problem because they are not in the same group or in the same column. What we do is just use two steps. Right? So you just go from SE to S. That is what kind of pattern? You go from SE to S is what? Increasing. So that's one step. You know what do we do? You do two steps. If two steps give you the same answer, then you get the same answer. If two steps give you different answer, then you cannot tell. Right? So from S to SE increases. What about from S to CL? Okay, so two steps both increases, therefore CL is larger than, have a larger electronegativity than SE. It's very confusing. Right? When we see model, you probably think about this as radius, and radius is opposite. Right? CL is smaller. Right? So then, what you can use this number. If I want to solve the problem, I will use this number. Then you just use this kind of not really a sharp line, kind of a guiding line. So you have this region. Okay? If you have the chemical bond, okay? For example, between H and Cl, you have the chemical bond. And then you have that electronegativity for H. You have the electronegativity for Cl. You just use the two numbers, find the difference. And that, if that is 0, that means the pure covalent. If, no, for HCl, obviously that's not. Right? Now, if it's somewhere between these two numbers, you call that non-polar covalent. And then you have some number between that, you call that polar covalent. And if it's larger than 2, you call that ionic. Got that? Now, that sometimes not always work so good with reliability. So sometimes we will use that percent ionic character to add a second check. So we'll talk about that later. So right now, you just remember these few regions. Right? See, when you number, you have the Cl to Cl bond, and obviously the difference between this Cl is 0. So therefore, it's a pure covalent. If you have something less than 0.4, not 0, you call that non-polar. But I usually will call that non-polar, even though the pure covalent is also non-polar. But that's just one more point. So this between H and Cl, you will find out the difference is 0.9, right? So that you call the polar covalent. And if you take that all the way to the other side, you take that Na with Cl, and Na is 0.9, Cl is 3.0, you get 2.1. That is more or equal to 2.0, you call that ionic. Now, ionic polar non-polar is a very important characteristic. So right now we just identify the bond is polar non-polar. So then in chapter 10 we will see the molecular. So people find out what is a polar molecular. So what does polar molecular do? Polar molecular will be attracted to some of those electrical charge. And hexane. Hexane is a kind of very similar as those octane, like the gasoline. They are non-polar. So they will not be attracted to those electrical charge. Right? Right? So then if you use those lines, use that these two difference, the electronegativity difference too, and you will miss a lot of those compounds that is ionic. Right? So what they did is to do a double check, second check. Okay? They use the so-called percent ionic characteristic. What that depends on this concept called the diagonal moment. Diagonal moment is that number. Okay, so that number U. Okay. That number U equals Q times R. R is similar as what we said in the lattice energy. It's the distance between the two atoms. Q is also similar. Okay? Q is the charge separation between the two sides. Right? And so then you can measure that, and you can also predict that. Okay? So that the percent ionic characteristic, okay, is kind of a percentage of the measured dipole moment compare what you will get if you totally take those separate those charges. So that tell really give you some of those kind of measurements, calculation. Okay? If you take this, here they said like 51% or higher, okay, is ionic. Okay? And that's assuming that Q1 times Q1 and Q2 are the same. Okay? So from the 51%, you pretty much can calculate 51% 0.5 equals Q1 times Q2, I say that equals x squared. So x squared equals that, and you will take x equals 0.51. That tells you is about 0.71. Okay? What does that mean? That means your charge, okay, on one maybe plus 0.71 electrical unit charge, on the other one is negative. That means you really not have to transfer the electron, one electron completely from this criterion. So that means if you transfer like 71%, then it's already ionic. Right, so that is about this this one. I think that you can use those patterns to finish the program. Okay? So let's see if I want to compare which one is more electron, which one is what the question? Determine the bond between needle pair is covalent and ionic. So what you have to use? You have to really use those numbers. If I tell the number for SI is 1, I tell the number for fluorine is 4, so you have to take 4 minus 1, get 3. And 3 tell you the compound, the bond is ionic. It's larger than 2. Now the other one between N and Cl, you take the N, the number for N is 3.0. The number for Cl is 3.0. So therefore there's no difference. Pure covalent. You can call that pure covalent, or you can call that non-polar. Like that? Very straightforward. So now you want to find the bond between N and O, no matter you are double bond or single bond, you have to take the number difference. So the N, the number for O is 3.5. The number for O is 3.0. The difference is 3.5. According to our rule, is a polar. Okay?
So that's given to us, right? We're not supposed to like.
Yeah, I will give it to you. I just know that kind of like those. Right. So then this question, I think this was the other CRE, right?
Yeah.
Okay. So what's the order? Increasing order of bond polarity, which pretty much is increasing delta En. Delta En. You know what is delta En? Right? It's the electronegativity difference. Right? So this one is 0. Right? What else? You compare this H with. So these two, then you compare this with this. I think this one will have a lot of difference, because this sodium is ionic. Right? So this was the smallest one. Smallest difference? Because they're the same. Okay, so find out that. Then you tell the difference between these two. And the difference between these two, this F is have a large number, 4. BR is 2.8. Right? Okay. Small one. Next small one. Next small one. Next large one. This one is the largest one. Right? You see the answer is what? The answer is D. Answer is D, and not D. Right? Right? Yeah, CRE, you can give you also the CRE for Chapter-8. Right? Hold on, yeah, give it to me like Thursday. Yeah, some of you already know.
For the final, how many questions are supposed to be on it?
70.
70?
70.
Okay, yeah, but what is that?
I think that is December 15th.
15.